Go ahead and get started. Today, we're actually going over more practice part 2, and it's a little bit different than the first worksheet that we had in that I'm actually giving you some charges to work with here. The homework for tonight is to do the review sheet, and some of you have already started on that, which is awesome. So let's take a look at the ones here. So again, what was different from yesterday is that we have some charges actually on here. And on the test, you'll see some charges. Sometimes you'll see some neutral. So be aware of what's happening when you actually have a charge. When you have a charge, when you have a charge on the thing. Also keep in mind that the value at the top, that's your mass. The value at the bottom, that's your protons. I'm still getting questions about what does the top number mean? What's the bottom number mean? And if I give you a symbol, or just the name, make sure you're going to the periodic table to find out how many protons the thing has. Unless I'm giving it to you here, then it's pretty safe. So again, take a look at this information, keeping in mind that if we have a positive charge, that means that you have more protons than you do electrons. If you have a negative charge, which we do down here, then that means that we have more electrons than protons. Protons do not change for that element. So if we're looking at iodine, we're always going to have 53 electrons. If we're looking at aluminum or aluminium, we're going to be looking at 13 electrons. That's what identifies what we're looking at. Questions on that? Okay. Let's take a look at 2. All right. Looking at 2. Now 2 was kind of interesting, and I didn't ask you to show this information, but it's probably not a bad idea to keep you from doing something strange. So Part A said how many protons, neutrons, electrons are in neutral sulfur-35. So again, if it's neutral, then your protons and your electrons should have the same value. You would have to go to the periodic table to find out how many protons you have for sulfur. So you'll have a periodic table tomorrow, and you'll get to use a Friday, and you'll get to use a calculator as well. So I went ahead and did a running total in all of these just to keep myself from doing something dumb. Part B says write the atomic symbol for sulfur-35 and what each of these numbers represents. And what I said yesterday is piggyback off. So when you get a value for A, use it, continue it in B, and then answer the question based on it all the way down. So again, the top number is your mass number, the bottom one's your protons, and then there's nothing over here on the right, but that's your charge. So when we have a charge, then we would put that in there. So still same values here because we didn't change anything. Part C says write a new atomic symbol when you remove 2 electrons. So going from 16 electrons to 14 electrons, going from 16 to 14 because we took 2 away. What do we have more of? Protons than we do neutrons. So that's why the charge is positive. Okay. And again, I did that just because some people were like, hey, when we take 2 electrons away, that makes it more negative. No, the proton number will remain the same. And then looking at part D, it says remove 1 neutron. So when we remove 1 neutron, I went ahead and did that, keeping in mind that when we add those 2 values together, that gives us our mass number. So the mass went from 35 to 34. Charge remains the same. The number of protons remains the same. Then in the part E, this is where it really hit the fan. A lot of people were, first of all, they were leaving the symbol the same, but changing the proton number. When the protons change, okay, and this is just theoretical, we're not doing any nuclear chem here, we're just saying we're going from 16 to 15. So now what are we looking at? We're no longer looking at sulfur, but we're now looking at phosphorus. Since we took a proton away, again, our mass is determined by how many protons and neutrons, so that value will be reduced by 1, as well as the protons. And the reason why I brought the electrons down so you could actually see, hey, there's 14 negative charges and only 15 positive charges. That's why my charge on the phosphorus is a +1. And if I were a betting man, I'd say at least 75% of you missed that. One of the components here was not correct. So make sure that you're actually taking your time on that, kind of evaluating it, and asking yourself that type of question. Questions on 2? 3 is very similar. Again, I did a running total. Ooh, what happened there? Okay, well, it kind of got butchered there. Okay, or for question 3. It said, look at the periodic table, find lead 203, 205. So again, I know my proton number is 82. How did I know that? I went to the periodic table and found that. So to 205 minus 82, hopefully that gave me 123. So again, just carried that values on just to help me not do anything dumb. So again, write the symbol, mass number on top, protons, since this is neutral, no charge. Part C says, write the new atomic symbol when you remove 4 electrons. So going from 82 to 78, my proton number remains the same, but taking away 4 negative charges gives me a +4 charge. Nothing else over here changes. So 82 and 205, those remain the same. Part D, write the new atomic symbol when you add 4 electrons. So when I add 4 electrons, my mass changes from 205 to 209, and my neutron number changes, but that's the only thing that will change is 209. Charges remain the same because neutrons are neutral. Good. And then write the new symbol when you add 2 protons. So again, adding 2 protons means that I'm adding to the mass. So my mass goes from 209 to 211. My proton number went from 82 to 84 because that tells me how many protons. My electrons didn't change, but my positive charge did, so I increased it by +2. Isn't that fun? And then looking at number 4, this was very similar to what we did in the homework. Make sure that you're moving the decimal place 2 times regardless of what you're looking at. Again, I still have some students that are just moving it in front of the first number. But if you don't move it 2 times, then you're going to get a number that's not the average or in between these guys here. So always do your check. Always evaluate your answer. First things first, make sure that your number that you get actually does fall between the 2. And then the next thing you want to do is ask yourself, okay, where's the heaviest or highest percentage? Well, for 64, it's the highest percentage, so our answer should be closer to that 64, and it is. So once you get that value, then go to the periodic table and ask yourself, which mass does that best represent for? And zinc was the closest one. Okay. And then 5 and 6 were very similar to 4, except it was in word form, which you guys just love. Love it. So number 5, again, we only had 2 isotopes. So you had your mass and then your percent. And what are these percents always supposed to add up to? 100. Yeah, so you have a 100% sample. Okay, it's kind of hard to work with something that's not 100%. That's kind of a segue into 6. But make sure that your percents actually add up to 100. If it's given to you, you're given all the percents, just double check, kind of eyeball and say, if I take 50 and 49, oh yeah, that's 100. And then again, your answer should fall between those 2, and it does so nicely. And then looking at number 6, 6 was fun because it gave you a percent for this one, gave you another percent for this one, but it did not give you a percent for the last one. And I had quite a few people come up and go, what do we do? Do that. Okay, always ask yourself that you need a 100% sample, so 92 plus the 5 gives you 97, and then so our missing is 3% there. And then from that, we can find out our value. Okay. So sometimes I won't give you, I'd only leave out one piece of information. I'm not going to rake you over the coal there. Does that one make a little more sense now? And then 7 and 8, those are just visiting the good times again back in the day. So density, mass over volume. Volume, milliliters is an acceptable unit for volume. So you could have centimeters cubed, milliliters. I've even seen it in liters. So as long as it doesn't specify a unit, this is good enough. And then percent error, we got our value here. This is what we got from the lab. So we'll do our lab value minus true, get a value here, and then divide it by the true. So we should get around 17.4. questions or any clarification on any of these? Okay. This one was fun because it did give a lot of different, or a lot more ways of doing these types of problems. And of course, you gotta love 3 and 4, or 2 and 3. Okay. All right, so tomorrow, hang on. So tomorrow's the test. And just as a refresher, what I mentioned yesterday, the more practice 1, more practice 2 that we worked on the last couple of days, in addition to the review sheet, those are great things to be looking at, as well as the notes for studying for the test. Bring your device tomorrow, make sure it's fully charged. Part of the test will be on the device, part of it will be on paper. Also bring a calculator tomorrow. Not your phone as your calculator, bring a calculator and a pencil. So we'll have it on both of them. And I think there's 45 or 46 questions. So it's pretty fun. All right, so let's go over this, and then if you have any other questions, by all means, we can clarify a few things. So the first thing, and what I was doing was I was just kind of giving you some questions to get you to go back into the notes, kind of dive back in. And I heard a lot of people yesterday say, well, what's a cathode ray? That's exactly why I wanted you to get back in the notes, so you could refresh the things that we had talked about a week ago. So just to get back in there. All right, so number 1 says, what are cathode rays? Why are they called cathode rays? Do the cathode rays have a charge? And if so, what is the charge? So the first thing is, cathode rays are a charged particle. And we know it's charged because it was influenced by a magnet. And we actually got to see that demo. The reason why they call them cathode rays is because it starts at the cathode end of the cathode ray tube and moves toward the anode. So the cathode is negatively charged, the anode is positively charged. You do not need to know that. All right. So what I want you to know about cathode rays are that they are charged particles, and that those cathode rays are made up of what? Electrons. Very good. So they're made up of electrons, and the charge on those are negative. That's what I want you to take away from the cathode rays. Who worked with the cathode rays? There's 3. We've got Dalton, Thompson, and Rutherford. Which one worked with the cathode rays? Okay. Dalton. No. So third choice? Thompson. So Thompson worked with the cathode rays. I'm glad I asked that question. So Rutherford worked with the gold foil experiment, and he used alpha particles, and Dalton was just sitting by the pond going, at him. Okay. Didn't do a whole lot there. But he gets credit for that. Okay. So sometimes being first is important, sometimes we'll see. All right, number 2, what are the differences in charges or charge among protons, neutrons, and electrons? So again, make sure you know those subatomic particles, where they're located, and what their charges are. So obviously, protons are positive, neutrons are neutral, electrons are negative. Now, make sure that we also know the relative differences in their masses as well, so that a proton and a neutron are pretty equivalent, and it's called an AMU, an atomic mass unit, which is equivalent to the mass of a proton or a neutron. Electrons do have mass, but it's so small we don't consider it. So we say that it's 0 AMU, but it's really 1/1840 to say that. So yeah, everything has mass that we are working with, but its electrons are so small. Number 3, a particular atom of potassium contains 19 protons, 19 electrons, 20 neutrons with the atomic number, the mass number, all that jazz. Make sure that you know how to make a symbol. All right. The mass is always on top, the protons are always on the bottom. That is different than what the periodic table that you'll get tomorrow is. And you'll know that the atomic number is the atomic number because it's smaller than the mass number. That will always be the case. Always. Now, I can rarely say always in here, but that will always be the case. Also, it's your option if you want no charge or 0 there, or put nothing. If you put nothing in the top right-hand corner, that is telling everybody that it's neutral. If you have a charge there, then you're indicating that it has a charge. But again, make sure that you're aware of what that top number is, the mass, and the bottom number is the protons, or the atomic number. Number 4 is similar to number 3. Probably not a bad idea to every once in a while write down the information that you are given or that you think you have to help you write the symbol down correctly. Okay. Just like with the homework the other day where I had the running total of the protons, neutrons, and electrons. That'll keep you out of trouble. Okay, Hector. This was not required. Is that what you're asking? You're a good man. I'm telling you. Did it? Oh, well then, good job. My bad. So, doing what you're supposed to. That's what I like to hear. But sometimes the question won't do that, and it's still a good idea to write it. So, thank you, Hunter. Yeah, you don't want to be lazy because when you're lazy, bad things happen. Remember that. All right, number 5. This is not one of your 52 elements, but that's okay. With homework, I can give you all kinds of things because you have Google, you have your friends that know all, 118 elements right now. So I don't mind that, but on the test, it'll be limited to your 52 elements, names, and symbols. But still, it's fun to look at uranium and the history behind it. Don't care. But make sure that you can answer how many protons, electrons, and write the symbol accordingly. Okay. Questions on that? Looking at number 6. Now, somebody did point out yesterday, like, are these neutral? And I was like, oh, yeah, I probably should have put that. On the test, I will identify if something's neutral or has a charge. But I was assuming that the reader would interpret that that was neutral. But that was a great question that somebody asked yesterday. However, don't freak out when you see a 14, a 32, 63, etc. Those masses will not be on the periodic table because these are isotopes. All right. So make sure you know what that dash 14 means. That is the mass, the protons plus neutrons. Same thing with all the other numbers behind there. I don't believe I asked you to write the symbol, but it's not a bad idea to get practice on that. So make sure you know what the mass number is. Yeah, Hunter, I'm sorry.
I just thought of this, but
yeah.
like if the atomic mass is the number of protons plus neutrons, why are all of them on the periodic table like crazy weird numbers?
Crazy weird because, like, carbon, for example, has carbon 11, carbon 12, carbon 14. So it's it's the average. Yeah, perfect. So there are.
That's like the chart thing that we did.
Segue. Nice. So getting into that, that's why we have all those isotopes and we get that number for the periodic table. Now this one isn't on the periodic table, but it's closest to. Anybody check and see? So that's what you get for that. I just caught you in La La Land. That's why I picked on. No, that one's actually closest to silver. But I didn't ask that. But a couple people were still asking about this today. Be sure to move the decimal 2 places, not just in front of the first number. All right. In some cases, it actually is in front of the first number. But as I said a couple times, make sure that your answer actually does fall between the high and the low. All right. Now, that's your first check. The second check is kind of evaluate and see where's the higher percentage at. Is it near the top, near the bottom? Near the bottom. So the 107 makes sense because a lot of the mass, or the majority of the mass, is near 108. Okay. So that's just the check. But the first one, absolute, make sure that it's actually in the middle, or I'm sorry, between the high and the low. Okay. A few terms here. Now, again, not all the terms that I want you to know are on here. These are just a few. Recall that at the beginning of the unit, I put the vocab at the beginning, so take a look at those again. But here's some that are very, very common. Like, what is an isotope? An isotope is just an atom that has the same number of protons, or atoms, I'm sorry, but they have different neutrons. So they have different mass values. Okay, so an isotope is, if I look at, say, something that has 7 protons, and it has 8 neutrons, well, that's an isotope for nitrogen. Okay. So make sure that you know what isotope is. Atomic number, that's your number of protons. So it's just another way to say that. And in the table, you'll notice that I had a column for protons and a column for atomic number. They're the same thing. Atomic mass, the only thing that we're using with the atomic mass is protons plus neutrons for what we're doing for individuals. Neutral atom is where you have the same number of electrons as protons. I didn't put it up here, but what's a cation? And some people are still calling it a cation. But what is a cation? What is a cation? Yeah. Ion. Good. So all that's fine. So remember, cats are very positive. Okay. So let's see, you get a wrong perception of the world. And I like that somebody said in first period, anion kind of sounds like antagonist, so that's bad. Cat's good. Antagonist bad. Okay. So if you have a cation, do you have more protons or do you have more electrons? More protons, good. And the proton number is locked, so electron values change. Okay, keep that in mind. As long as we're looking at the same element, then the electrons will change. Atomic mass unit, that is simply the mass for one proton or one neutron. You're never going to have to memorize that mass. I don't care. That's worthless information. It's really small. That's what I want you to know. It's really, really small. Okay. The mass, the 1.67 times 10 to the whatever, negative 24. Matter here. Okay. All right, cathode rays. We actually already talked about those, but those are the particles that Thompson used in his experiments to identify electrons and modify his atom, or his model of the atom. Just while we're talking about models, if we were to look at, say, Dalton's model, what did his model look like? Yeah, so it was a sphere or a ball, and it had a consistent density throughout, or there was nothing in it, so to speak. When you look at Thompson, old JJ, okay, what did his model look like? Yeah, so it's a plum pie pudding. So you got the pie pan filled with pudding in there, and then you plop some plums in there, and they're supposed to represent those things. So there's nothing centrally located. That's probably the better way to think about it. And then Rutherford, what did Rutherford say? That's the marble in the middle of the football stadium. Okay. So a centrally located dense core that should be centrally located instead of offset. Looks more like a focal point. Okay. So make sure you know those models. This is not the final model. We'll talk about Bohr's atom a little bit later on, but this is where we're at. So we have in Thompson, we have protons and electrons. Notice no neutrons. Okay. And they're very random. No centrally located. Look at Rutherford. What do we have in Rutherford's model? What particles? Do we have protons? Yes. Okay, so we're still carrying the same information. But the electrons, how do the electrons? They're buzzing around like bees around a hive. Very random. Okay. That's the model that Rutherford had. We'll talk about that later. Yeah, sorry, Cam. He did not. Yeah. Neutrons came after Rutherford came up with his model, and then he integrated it in. Dalton had a ball. That's it. No subatomic particles. He didn't know about electrons, protons, or anything. Don't ask how. Yeah, that's a good question. And then he came up with all these theories about how they're indivisible and how they make whole number ratios. That was alien talk there. All right, and so Rutherford again has protons and neutrons in there. All right, so looking at the table, go ahead and check that. Again, keeping in mind that atomic number and protons represent the same thing. So when you look at atomic number protons, it better be the same as that value in the bottom. Okay. And there should be a +1 here. Your eyes are playing tricks on you. Okay. take a peek at that. And be sure that you can actually answer the information. You will be given a periodic table so that you can identify. If I were to just give you the atomic number, then you could go and find the symbol. Keeping in mind that I will only give you the 52 that you know and love and will miss when you leave here. I know. No. The 52 we use in here are the same 52 we use in AP, and the same 52 you'll probably use in college. They might clean it up to 50. You know one of them. Uranium. The other ones like Einsteinium, Berkelium, those are garbage. We don't care about that. That was somebody's pet project. Look what I made. It lasts that long. It's garbage. Exactly. Garbage. We don't care. All right. So, any questions? Need any clarifications with the table? Good. All right. So, here are some things to know for the test. Again, this is not everything, but it's a good thing to know. So, make sure you know the difference between Dalton, Thompson's, Rutherford's model. We just did that a second ago. Of course, know your 52 elements, names, and symbols. Never not know that. Number 3, make sure that you can calculate the average atomic mass and identify the element. That's what we had with the table. Now, I may give it to you in word form. That's always fun. Remember that? Like yesterday, I think it was questions 5 and 6. Can't remember. Maybe 4, 5, and 6. Maybe somewhere around it. Okay. Here we go. Law of conservation of mass. What's that mean? Good. So we're not in the business of creating or destroying things. Good. When we talk about law of definite proportions, this is saying that if I have a molecule of carbon dioxide, I go to Pluto and find what I think is carbon dioxide. It better have that. What is not on here is law of multiple proportions. Multiple proportions says, okay, I've got this carbon dioxide, but I also could have carbon monoxide, I could have carbonate, I could have oxalate, I could have a lot of things from this carbon and oxygen combination. So there are multiple combinations. When I talk about definite, that is definitely carbon dioxide. 1 carbon, 2 oxygen. Okay? So multiple just means that if I have carbon and oxygen, I can make a lot of different things. But definite is locked in. Does that make sense? Maybe. All right. Make sure you know the difference between atomic number and mass number. So atomic number. What's the atomic number? Protons. Mass number. Good. Make sure you know how to correctly write the element symbol. So mass is on top, protons on the bottom. Correct symbol, and then charge if you have one. Okay. Know the significance of Thompson's experiments. Why did Thompson do that? The cathode rays? Yeah, no. He found subatomic particles. Very good. That's the Cliff Notes version. And then, what is the significance of Rutherford's gold foil experiment? Yeah. Yeah, so that when we look at the model of the atom, so it's mostly empty space, well, that's a little better, but that 99.9% of the mass is located right there in the middle, centrally located core. So it helped to validate that if I had a smart car and a tractor trailer with concrete blocks, that it would obliterate that smart car instead of bounce back. Or if I held the tissue paper and somebody fired a cannonball at my face would be gone. What a sad, sad thing. Beautiful. All right. Make sure that you know cations, anions, and be able to determine the charge. Okay. Any other things that you can think of